Hello everyone, so I hope you're doing okay. Today I'm going to talk about denitrification. So I'm going to try to share my screen with you here. All right, so let's talk about denitrification. So let's see if I can get, here we go, get my cursor here. So denitrification, first we need to look at the nitrogen oxidation states and kind of better understand those so that we can understand what's happening in our system with either nitrification or denitrification. So one of the things that I didn't put on here but could be added would be organic sources of nitrogen. So something like biomass or wastewater, things like that. And those typically have a -3 oxidation state for the nitrogen. And so what happens first, if those undergo degradation processes, they don't change the oxidation state, but they do release ammonium. So they release ammonium groups from the organic nitrogen. And so that process is typically called ammonification, where we're producing ammonia from an organic source of carbon. But we're not really changing the oxidation state of the nitrogen. It's still in a -3 oxidation state. So what we first learned about was nitrification, and that's where we take our ammonium, and the first step is going all the way from ammonium to nitrite, and that's done with our nitrosifiers, and then our nitrifiers pick up and take that nitrite and convert that into nitrate. So this is an oxidation process that takes us from a -3 oxidation state of the nitrogen all the way to a +3 in our first step, and then up to +5 in our nitrogen oxidation state. So once we've kind of converted all of our ammonium to nitrate, then we can go through our denitrification process. And that starts with nitrate. It goes back to nitrite. And then from there, it goes to NO and 2O, and then our nitrogen gas, which is at a 0 oxidation state. And from there, this is a gas that can then be released into the atmosphere, and it's not harmful. In fact, most of our air that we breathe is made up of nitrogen itself. So that's how we remove the nitrogen from the wastewater. We essentially convert it into this nitrogen gas that's then released. There's an interesting process called anammox, and this was kind of discovered when this new type of microorganism was found in, I believe, a trench in the ocean. And they discovered that it could do this really kind of unique metabolism where it takes an ammonium and it takes a nitrite, and it converts both of those into nitrogen gas. So what's happening is it's it's oxidizing the ammonium while it's reducing the nitrite and ending up with nitrogen gas. So this is actually really helpful because some processes now in wastewater treatment will take and do partial nitrification. So it'll take ammonium, go to our nitrite and stop there. So they have to be very careful with the process controls and how much dissolved oxygen is provided, because they don't want to go all the way to nitrate. They want to stop at some amount of nitrite with some amount of ammonium still left. And then they can move into this anammox process without having to provide all of the oxygen that's required to go from nitrate to nitrate, and then also provide carbon source, which we'll talk about in a minute, to make sure that denitrification moves down to the nitrogen gas. And so in this case, we have kind of an interesting process where we can do partial nitrification take this nitrite and ammonium that's still left over and use it in this anammox process to be able to produce nitrogen. But we'll talk in another video a little bit more about some of these unique methods of removing nitrogen from wastewater. But for this, the purposes of this video, we're going to talk mostly about just denitrification. All right, so what does the traditional denitrification or nitrification denitrification process look like? Well, essentially we start off with ammonium, and we're adding oxygen to get it to nitrite, keep adding more oxygen to get it to nitrate, and then now we have to start adding carbon sources because during this process, this nitrification usually occurs after we've already had the heterotrophs consume a lot of the COD or BOD organic matter. Because recall that COD, that carbonaceous oxygen demand, is satisfied first. And so we pretty much consume most of the carbon during that process. And so then if we continually extend the aeration process, so we have extended aeration, we can use the additional oxygen now to satisfy this nitrogenous oxygen demand. So this is really representing just the nitrogenous oxygen demand that occurs after we've satisfied our carbonaceous oxygen demand. And so now when we end up here with our nitrate, we're pretty low at this point on our organic matter or carbon source. And we switch to sort of an anoxic operation where we don't provide any more oxygen because we don't want that to compete as an electron acceptor, but we do have to add some carbon now so that we can force the nitrate to nitrite and then add some more carbon so that we can get it all the way down to nitrogen gas at the end. And so the goal is to get everything in nitrogen gas so that that can be released to the atmosphere and removed from the wastewater. So where do we typically put this within our treatment train? Well, essentially we have our inlet works, our primary settling, and we typically put our system right around the activated sludge. So you can think of this nitrification tank as both an activated sludge that removes BOD, but also has extended aeration so that we can also do nitrification. And so once we do nitrification, we get most of our nitrogen in the form of nitrate. We can go to this denitrification tank and we can remove the source of oxygen. And here we will maybe possibly add some carbon source to it if needed. And we'll force the nitrate to be converted all the way to nitrogen gas for release. And then from there, our effluent goes to secondary settling and so forth. So the system is typically centered right around our activated sludge. There's different configurations that have been used, but this is kind of the most typical treatment method that you'll see for traditional activated sludge, traditional biological treatment system. Okay, so denitrification is a form of anaerobic respiration. So what does that mean? Well, if you think about us as humans, we do aerobic respiration, meaning we breathe in oxygen and we use that as our electron acceptor, if you will. And we do respiration using that. This is a form of anaerobic respiration, meaning that there is no oxygen involved, but they are still breathing it, if you will, and using it as an electron acceptor. So in this case, our forms of electron acceptors are nitrate and nitrite. So those are the most, the typical electron acceptors for these, for this form of anaerobic respiration. And the denitrifiers are facultative. And so what does that mean? That means that they have a metabolism that they can survive in oxygen conditions. So if they have oxygen around, they'll preferentially use that oxygen and save only the nitrate and nitrite for electron acceptors under conditions where they don't have oxygen. So we have to make sure that we are providing the right conditions for these microorganisms to do denitrification. And so in that case, we make sure that we remove any sort of oxygen. Most of these denitrifiers are heterotrophic, but there are some autotrophic. What does that mean? Heterotrophic microorganisms use organic carbon for their carbon source, but there are some denitrifiers that we know of that are autotrophic, meaning that they use inorganic carbon or essentially CO2 for their carbon source. So the steps in denitrification. First, we start with nitrate, and then we move to nitrite, then we move to nitric oxide, then to nitrous oxide, and then to nitrogen gas. And so we want to make sure that there's enough carbon, enough organics to basically push all the nitrate all the way down to nitrogen gas here. If we don't have enough, we may get stuck with some of these intermediates, which I'll talk about in just a minute here. So important considerations for denitrification. We need to make sure we have enough organic matter. So for example, if we have too little organic matter, intermediates like nitrous oxide and nitric oxide can accumulate, and that's not a good thing. So even though this is a gas and could be removed from the system and accomplish our nitrogen removal from the wastewater, we don't want to get stuck with those because they are greenhouse gases. And so we don't want to be contributing to greenhouse gas emissions. And of course, especially nitrous oxide here is a very potent greenhouse gas. And so we want to make sure that we're not getting stuck with these intermediates and that we are providing enough organic matter to push the denitrification process all the way through to nitrogen production. If we add too much organic matter, for example, ammonia production occurs instead. And so what that means is that we have too much organic matter, it's just decomposing, and ammonium groups are coming off of the organic matter instead of being utilized as a carbon source for the denitrification. And so why that's a bad thing, if we go back to our nitrogen oxidation state, during denitrification, we're going towards the left, so from right to left down this oxidation state axis here. So we start with the more oxidized and go down towards the more reduced. And the problem is, if we have too much organic matter, we end up producing this ammonium. And notice there's nothing to the left of that ammonium, so there's nowhere for that to go. So we end up accumulating this ammonium because we're under reducing conditions, we're only going towards the left. And notice the goal is to get to our nitrogen gas, which is actually to the right of the ammonium. So we would, if that occurred, we'd need to have that wastewater go all the way through the nitrification process and then go to denitrification in order to remove that ammonium. So we don't want to add too much organics during the denitrification process and end up with ammonium that's stuck and can accumulate. Okay, so how much COD or organic matter do we need to add? Well, if we do the stoichiometry, our theoretical COD that's required is 2.86 grams of COD per gram nitrate as nitrogen. And so we can use that as a good starting place for developing or determining how much electron donor we need to add if we need to do that, and so forth. So oxygen, of course, is undesirable because it competes as an electron acceptor and it'll be used first. So remember, those denitrifiers are facultative, meaning they can also use oxygen, and they get more energy out of using the oxygen. If you recall our electron tower, they will get far more energy from using the oxygen as an electron acceptor, so they'll switch to that metabolism and utilize the oxygen first, meaning we are not achieving any denitrification. So we need to make sure that the oxygen is excluded so that they switch their metabolism to the denitrification metabolism. We also have to be very careful about our pH, for example. During nitrification, we do have a loss of alkalinity. And so that's something that, we often will calculate and figure out, well, how much alkalinity is lost during nitrification. And then when the wastewater is transferred to denitrification, we actually get some alkalinity back. However, only about half of the alkalinity that was lost during nitrification is replaced during denitrification. So we may need to add additional alkalinity to our wastewater following denitrification to make sure that we have the proper amount of alkalinity and we can maintain a stable and neutral pH. And then, of course, this process, the denitrification process, is very temperature sensitive. And so that means that we will need to, take that into account if we're designing, for example, a denitrification system that is for a colder region or a region where they see seasonal fluctuations of temperature that are very significant. Okay, so we have certain sources of external electron donors that we utilize. So recall that after, our BOD is removed, and then we go through extended aeration. We have mostly just nitrate and very little electron donor. And so oftentimes we have to use, supplement or add an external electron donor to be able to drive the denitrification process. So some of those that we often use, methanol is a very popular, common source of electrons that we add. Sugars, ethanol, acetic acid or acetate, acetone, and even sometimes methane will be used. And the things that we really are looking for in having an external electron donor is that we're looking for something that's highly reduced. So we don't want something that has to go through the reduction process already. So if it's highly oxidized, then there is going to be very, few electrons that it can accept and so forth, or electrons that it can donate rather and so forth. So we want it to be highly reduced. We want low carbon so that the biomass yield is low and that most electron equivalents are used for energy. So some may say that, well, why not put hydrogen in as an electron donor? Well, we also want it to be easy to handle, and unfortunately, unless we're producing hydrogen on site, it's often not a good idea to store large amounts of it to use as an electron donor because of the issues of storage and explosive properties and, risk of fire and explosion, things like that. But we also want something that's low toxicity, so we want something that's not going to be a toxic or disruptive electron donor so that we can add it to the biological system without having issues there. All right, just a quick comparison here. So with our nitrification, we have a process condition that's aerobic. Whereas with denitrification, we have an anoxic process, so no oxygen. With our nitrification, we have organics, and similarly with denitrification, but sometimes we have to add those. Our electron acceptors, oxygen for our nitrification. For denitrification, our electron acceptor is nitrate and nitrate. Our carbon source for our nitrifications, organics for heterotrophs, and organics for heterotrophs for the denitrifiers, but also we can have some inorganics for the autotrophs as well. And for nitrification, we typically don't need to add an external electron donor, but sometimes we do for our denitrification because by that point in time, we've consumed most of the COD or BOD in the wastewater. All right, so that concludes this brief video on denitrification. Keep an eye out for another video on some of the other interesting nitrogen processes that are a little bit more novel and new that we're now applying to wastewater treatment. And I please let me know if you have any questions that I can answer about this. Thanks.